from the world's wildest waters.
It was incredibly deep water. It was deeper than the North Sea, a lot of it.
To its mightiest mountains.
If someone said to build a train through these mountains, you would think they're crazy.
Railways have set out to conquer them all.
I can't imagine how they could build this line. It's one of the most impossible railways.
I'm actually a little bit speechless. It's awesome.
Driven by daring engineers, for whom no obstacle
This is my kind of fun now.
is too great.
I truly love this structure. It's magnificent.
For over 150 years, our railways have been pushing engineering to its limits in order to open up our world. Driven by progress and a thirst for adventure, trains can now travel further and climb higher than ever before. But for train engineers, there's one ambition that's perhaps their biggest driving force of all: the need for speed. Shaping the iconic machines of the past, producing innovations for the future. But making trains go faster poses a unique set of challenges.
If you hit very many speed bumps at these ultra-high velocities, you will not survive.
When you have a train very powerful and very light, you need a special balance between grip and power.
When our train rush into the tunnel with high speed, the shockwave on the exit, we can get a big bang.
The trouble with most trains is they only have one engine. So the longer you make them, the loco must take the strain.
Hello.
But if there's a need for speed, there's only so big an engine can be. The birth of our railways and the steam locomotive go hand in hand. For over a century, across the world, these iron workhorses graced our rails. But by the 1930s, in the UK, these mighty machines faced a seemingly impossible challenge. They needed to go faster. As rail journalist Tom Bright is finding out.
Passengers at the time wanted their trains to be faster, more comfortable and more luxurious. So they introduced more facilities on their trains, such as dining cars and luxury saloons. But that meant trains got heavier and therefore slower.
The once thriving rail networks were under threat from newer, faster road travel, and the rail companies were fighting for fares. The most hotly contested route was between the two great capitals, London to Edinburgh. To make this near 650-kilometre journey at speed in a steam train weighing several hundred tons would require a locomotive like no other. And in 1935, it was the A4 Pacific class that would change everything.
They brought improvements in speed and power that the world had never seen before. The A4s were the ultimate in express passenger locomotives.
Its designer was one of Britain's great railway pioneers, Sir Nigel Gresley. Gresley had already designed the legendary Flying Scotsman, an A3 class locomotive.
What Gresley did with the A4s was bring together all his existing ideas. In effect, the A4 is an A3 GTI, a souped-up A3.
The secret to the A4's power is the unique combination of innovations.
He was really pushing boundaries. The A4s he opted to have 3 cylinders. With 2 cylinders, the locomotive tends to wobble at speed. With 3, it's much more balanced.
Gresley's 3-cylinder formation produced smooth power, and the wheel configuration made the most of it. 4 small at the front, followed by 6 enormous driving wheels, giving 50% better grip, and 2 smaller rear wheels, which allowed space for a larger firebox. It meant more steam, more power, and so much more speed. After recent significant repairs, today a group of engineers and enthusiasts are firing up the Union of South Africa, one of only 6 remaining A4 super engines.
Needs just a little bit more, mate. About 3/4 full.
And it's a rare return to service for this 80-year-old powerhouse.
Basically, we're lighting the fire. So we've laid coal in there, we've put wood on top, and now we're using paraffin-soaked rags on top of that to get everything going.
Main priority is water's in the boiler. We definitely need water in there. Make sure it's fit to run, really.
Shut the top, please.
When you're pulling away, you've got to be very, very gentle with the regulator. It's got so much power, it will spin straight away if you gave it everything. Here, we're only, unfortunately, allowed to do 25 miles an hour. You're having to hold it back, really. It's such a powerful beast.
For today's trip, they're joined by the Union of South Africa's owner of 50 years, John Cameron. And it's an anxious wait, hoping that his antique train has still got what it takes.
That's one of my concerns, that it's working and that it won't fail. It won't sit down, as we say.
There are hundreds of rail fans hoping for the experience of a lifetime.
That sound you can hear is the singing that you want to hear, so you know the injector's on. Once you've got that, then you know you've got your injector on.
There's a lot riding on this mighty machine's historic engineering still working.
Well, you know, you've a lot of power at your command, so you've got to use it sensibly.
Trying to get a feel for the regulator. Shortening the cut-off so we don't need so much steam.
You always have to know your locomotive and know how it's going to respond, whether you're starting off, running at speed or braking. I mean, there's no 2 locomotives behave the same, even though they're the same class.
Gresley had created an engine of immense power. But before he could test it out, there was one more problem to overcome: the shape of the nose.
Gresley took his formative design into the wind tunnel. This is something that had never really been done on locomotives before.
The traditional flat nose was replaced with a wedge-shaped nose to decrease wind resistance, but crucially, lift the smoke and steam away from the cab. In 1938, equipped with this perfect blend of engineering, the A4's Mallard reached 126 miles per hour, becoming the world's fastest steam train, a record that still stands to this day. Gresley's A4 design easily outstripped his competitors in both speed and style. Passengers could now travel on the East Coast Main Line from King's Cross to Edinburgh in only 6 hours. And today's run has done the team proud. Gresley's super high-powered design achieved the impossible. The speed of the mighty A4 locos helped revive the railway, bringing passengers back on board. And his creation still continues to amaze to this day.
Union of South Africa really is one of the best. She is absolutely lovely.
But some railways' need for speed are out of this world.
In total, we've broken the land speed record 7 times and currently hold it at over 8 times the speed of sound.
Calling for more impossible railways. Speed, the ultimate ambition for some of the world's greatest railways. posing engineering problems that require new solutions. If speed is the only goal, come on! The faster you go, the bigger the problems. Any curve is out of the question. Even the tiniest bump has to be ironed out. And then, of course, stopping can be the biggest challenge of all.
Uh-oh.
The Tularosa Basin in New Mexico is a vast, isolated wilderness. But it is also the unlikely setting for a record-breaking railway. Hidden in the depths of the desert lies one of the most extreme rail tracks on the planet.
We're at Holloman Air Force Base, New Mexico, at the high-speed test track, where we push the bounds of speed. And we use this, the most incredible railway in the world.
Built in 1949 to trial new aviation technology, this extraordinary 16-kilometer rail line pioneers extreme speed, propelling its rocket sleds to around 2,900 meters per second.
In total, we've broken the land speed record 7 times and currently hold it at over 8 times the speed of sound. It's no exaggeration to say we make history here.
But with the sleds covering the equivalent of over 30 football pitches per second, the engineering challenges are seemingly impossible. If the railway track isn't perfectly engineered, the consequences will be catastrophic.
Any deviation in that rail is an impact load. It's basically like a speed bump in a parking lot. And if you hit very many speed bumps at these ultra-high velocities, you will not survive.
The extreme range of desert temperatures means the rails must be pre-tensioned to avoid any expansion and contraction. The continuous welding along the 16-kilometer length ensures arrow-like straightness. But all of this is secondary to the most crucial engineering of all: the challenge of making sure each sled sets out and sustains a perfect trajectory.
This sled's going to be tested at Mach 4. In order to survive and maintain its path down the track, the sled has to be aligned to within a few thousandths of an inch. Failure to maintain that alignment could result in the sled exiting the rail. It could destroy the track. The way that we maintain that is we use a laser 3D tracker to verify its alignment.
With over 10,000 test runs completed on this phenomenal railway, the test track sled park is the resting place for speed machines once used to test vital areas, such as parachute deployment and pilot ejector seats.
So we've got the A-10, F-15, F-16 here that all run down here at the track. Right here behind us, we've got the Sonic Wind replica. This is an example of the sled that ran down the track, specifically designed to see the factors affiliated with undergoing large Gs.
In the 1950s, the Sonic Wind No. 1 was piloted by Lieutenant Colonel John Stapp. His goal? To establish the effects of extreme acceleration and deceleration on the human body. In 1954, a 1,017-kilometer-an-hour run made him the fastest man on Earth. Incredibly, from this mind-blowing top speed, he was brought to a standstill in under 1.5 seconds, thanks to an innovative solution: a water trough braking system positioned within the track.
He basically underwent up to 40 Gs of deceleration during his last ride.
Battered and bruised, Stapp's mission was nonetheless an important milestone in improving safety for airmen and pilots. Today, unmanned sleds reach almost 10 times the speed of Stapp. Although this rail line is precisely engineered, the sleds themselves require a genius innovation to survive the brutal stresses of a run.
We don't use wheels because of the ultra-high speeds that we travel at. You simply couldn't keep the sled on the track. So what we use are slippers.
Attached to the bottom of the sled, the metal slippers are curved around the head of the rail. As the sled gains speed after launch, aerodynamic forces lift the sled from the rails until it's stopped by the slipper.
So once a sled takes off, it doesn't actually slide on the rail. It kind of floats. There's very little contact with the rail. A good example is if you ride a new modern roller coaster, it's a very smooth ride. But if you ride an old wheeled roller coaster, it's a really bumpy, rough ride. And that's exactly what the sled experiences out on the track.
For over 60 years, this game-changing railway has achieved what was once thought beyond the realms of possibility. And it seems, for the Holloman high-speed test track, the sky's the limit.
So the next goal is Mach 10. Just to put it in perspective, that's going from this point to the very north end, 10 miles away, in about 5 seconds. So anyone that needs to go fast, they look to the Holloman high-speed test track.
I believe this is the most incredible railway in the world. I wouldn't want to be anywhere else.
When speed is top of the agenda, railway engineers undoubtedly face some of their toughest challenges, and none more so than the lie of the land. It was the challenging terrain of Britain's South Devon coast that drove pioneering engineer Isambard Kingdom Brunel to create an extraordinary super-fast railway experiment.
So it's 1844, the railway had just made its way, edging closer and closer to the west of England. Brunel then wanted to take it further. He wanted to get his track all the way down to Plymouth.
But with a long stretch from Newton Abbot to Plymouth, renowned for its hills, Brunel had concerns that traditional locomotives would struggle with the steep gradients. To create power and speed, his solution was a recently developed concept: the atmospheric railway.
So the atmospheric railway was based on the principle that you can propel an object using atmospheric pressure if you create a vacuum in front of it, so it will propel itself forward.
Doing away with the locomotive, Brunel attached a piston from a carriage into a sealed tube between the railway's tracks. A pumping station positioned along the line pulled the air out of the tube, creating a vacuum in front of the train. Atmospheric pressure behind then acted on the piston, providing motive force, pushing the carriage along the track.
Here we have one of the largest remaining pieces from the atmospheric railway itself. Each section is 10 foot long. Inside here, this is where the air would have been. And we've got the slit in the top, which is where the piston from the carriage would have come all the way down.
Air leaking out of the slot was a major problem. The solution was to fit a leather flap along its entire length. As a malleable material, small wheels would reseal the slot once the piston had moved on. It was undoubtedly an ambitious design, but proved incredibly fast for its day, propelling its carriages to almost 110 kilometers an hour. The atmospheric railway's speed and ability to travel uphill offered exciting potential, but it had an Achilles heel. The slot's leather flap attracted gnawing rats, and consequently, sealing the system proved virtually impossible. As costs spiraled, after just a year, the line reverted to traditional locomotives. But almost 170 years on, in Northern California, Brunel's atmospheric dream lives on.
This is the Vector 1/6 scale test track. The track is about 2,000 feet long, a little over 600 meters, and it runs at about 30 miles an hour, which scales up to about 180 miles an hour in the full-size version.
Complete with graded hills and 180-degree curve, Eric and Max Schlinger's futuristic railway signals what they hope will be the revival of the atmospheric technology.
Basically, we did exactly the same thing that they had done in England. However, at the same time, we were working on high-strength magnets and found that we could do a lot of things they weren't able to do in the 1840s.
Whereas Brunel's tube ultimately failed because of its leaky leather-lined slot, the Vector's tube can remain permanently sealed thanks to magnets, which attract the train to the piston.
So what we have that Brunel did not have is the high-strength magnets that we use to couple the thrust carriage to the passenger car itself. That magnet is really what makes the system work, and when we combine that by coupling the passenger car to the thrust carriage, we now have a system that moves on atmospheric pressure. So now that we have it coupled, all we really need to do is add a bit of air pressure, and the train moves.
When scaled up, the pilot model uses the same principles of pressure adopted by Brunel. And with no locomotive or traction motors on board, minimal weight produces impressive speed.
This train doesn't have an engine on board, nor does it carry any fuel. Instead, we have a pumping station like this one. The pumping station provides either a vacuum in front of the train to pull it, or a pressure behind to push it. And that is where our force comes from.
And since all of our pumping systems are stationary, we can use a large variety of fuels. In fact, we think that there would even be a possibility of mounting solar panels along the edges of the tracks.
In full-scale production, Max and Eric believe the elevated Vector could propel up to 800 passengers to speeds in excess of 290 kilometers per hour. And because the train doesn't rely on traction, as with Brunel's creation, it appears to be an effective solution for climbing hills.
The advantage of the atmospheric rail is it eliminates the dependence of steel-on-steel friction. Consequently, we can go up or down grades that are steeper than traditional rails can handle.
All in all, this pioneering innovation is reviving a forgotten technology from the past, one that could help shape the future of the railways.
I just hope it happens in my lifetime, but if it doesn't, the people are a lot younger. I think they'll be able to pull it off.
This is the future of rail.
But creating the fast trains of tomorrow means overcoming a whole host of problems.
When our train goes rushing to the tunnel with high speed, on the exit, we can get a big bang, doggone.
It takes many inspired solutions to create impossible railways. Railways are picking up speed, with record-breaking trains pushing innovation to the brink and beyond. But with great speed comes even greater problems, requiring inspired engineering solutions. Japan, a land of islands and mountainous terrain. Building an effective transport network across this spectacular landscape has historically been a problem, and travelling across country extremely slow. In 1940, Japanese engineers set themselves the seemingly impossible challenge of creating a high-speed rail network. And finally, in 1964, they introduced the bullet train.
The influence of the Tokaido Shinkansen is vivid to the Japanese society.
The bullet train, or Shinkansen as it's known in Japan, was the world's first high-speed train. This powerful, streamlined machine could travel an unprecedented 210 kilometers an hour, and the country was transformed. Dr. Eiji Nakatsu was general manager of the Technical Development Department.
In 1964, after the opening of the Tokaido Shinkansen, we can have so many passengers, tourism and business trips. The airline between Tokyo and Osaka was demolished, and motorways utilization was also temporarily decreased.
The 515-kilometer journey between Tokyo and Osaka in the Tokaido Shinkansen was now possible in just 4 hours, as opposed to the previous 6.5 hours. But it wouldn't take long before Japan wanted to go even faster.
The first, of the beginning of the Tokaido Shinkansen, the maximum speed 210 km per hour. After that, we have tried to realize the speed up to 120 km per hour or 270 km per hour.
But increasing the speed of these super trains created an unexpected phenomenon.
When our train goes rush into the tunnel with high speed, the shockwave stand up and go to the exit of the tunnel. And on the exit, we can get a big bang, dogan, like that. And also, this pressure wave spread in all directions.
Like a piston in a cylinder, as the train sped into a tunnel, it generated atmospheric pressure waves, forcing the air out of the tunnel exit at the speed of sound, creating what's known as tunnel boom.
For the people on the line, these noises became a big problem because from 6 o'clock in the morning, early morning until midnight, they were suffered from these noises.
Homes as far away as 400 meters were affected by the ceaseless noise. And if trains were to go faster, it would only get worse. So how do you keep up with the demand for more speed and at the same time reduce the noise pollution? The answer came in the form of the newly designed 500 series. Designed by Dr. Nakatsu, he created a revolutionary new shape inspired by nature.
I am a bird watcher. My hobby is bird watching. Kingfisher jump into water to catch game from the air with lower resistance and into water with higher resistance. This is very similar to the train set rush into tunnel. That gave me a good idea.
A kingfisher dives into the water at high speed. And even though water is 800 times denser than air, it barely makes a splash. The kingfisher's streamlined success lies with the shape of its bill.
I realized that kingfisher could be a good inspiration for our head shape of the Shinkansen trains.
The new 15-meter nose cone almost exactly replicated the bird's bill shape, producing remarkable results. Introduced in 1997, these new super trains had 30% less air pressure resistance and could reach the record-breaking speed of 300 kilometers per hour. And the tunnel boom was dramatically reduced. It was a major breakthrough in fast train engineering, setting a template for the future.
This project was not made by myself. So many staffs or the personals worked together for this project. And I am proud of it. And this train set 503 gave a good influence not only Japan but also all over the world.
The bullet train is an undisputed high-speed icon. Since 1964, it's been refined several times over, getting quicker each time. But the latest bullet train engineers have turned their attention to the fastest technology of all, maglev. Still in its trial phase, the new magnetic levitating bullet train has surpassed 600 kilometers an hour. This frictionless train hovers above the guideway and relies upon the properties of superconductors for its extreme performance. Physicist Andrew Steele explains.
A superconductor like this one is a material that has no electrical resistance when it's cooled below a certain critical temperature. So when we get this down to minus 200 degrees, it's going to conduct electricity but without losing any energy. So if I drop it into nitrogen, that's cooling it down to that incredibly low temperature. When you bring it near to the magnets, it sets up an electrical current inside the superconductor, which keeps it levitating there. But that electrical current is stopped as soon as the superconductor gets above that critical temperature.
But if the superconductor remains cold in its superconductive state, the current will continue to flow almost indefinitely, creating an intense magnetic field.
We can use a principle very similar to this to try and make an example of a frictionless transport system. Here we've got some liquid nitrogen again. We just pour the nitrogen onto the superconductor. And because the superconductor is being cooled down really close to those strong magnets, it memorizes the magnetic field that it's cooled down near. And that means that it wants to stay in the same position relative to those magnets. So since the magnetism is the same all the way around the track, that means that it'll be stuck to this particular path. If I give it a little push, it'll go around and around for a very long time. So you can see that this kind of electromagnetic levitation with superconductors allows us to create a friction-free transport system.
And it's this friction-free technology that allows the Japanese maglev to break records. On board, superconductive magnets cooled with liquid helium to minus 269 degrees Celsius are used to both levitate and propel the train. It's hoped service will begin in 2027, with eventual travel time between Tokyo and Osaka just over an hour. A far cry from the 6.5-hour rail journey of the past, once more securing Shinkansen status as fastest in the world.
I think the Shinkansen are the most iconic railways on the history of the railways.
But achieving and maintaining great speed means balancing great forces.
When you have a train very powerful and very light, you need a special balance between grip and power.
Pushing rail engineering to its limits. One thing has always been a key driving force in the development of railways: the pursuit of speed. While engineers have tried everything, from slick design to slice through the atmosphere, to good old-fashioned brute force, or even tearing up the rule books altogether. In order to create a truly 21st century speed machine, no single stone can be left unturned. Italy. While this country might be renowned for its age-old landscape and for its ancient history, it cannot afford to live in the past. But its drive to be a thriving modern nation faces a seemingly impossible geographic challenge. Italy's 4 largest cities of Turin, Milan, Rome and Naples are spread out across the length of the country, making travel arduous. The only solution to keep commerce flowing: speed. Italy is the home of Europe's newest and fastest train.
We're standing in front of the Frecciarossa Mille, which is the high-tech gem of Trenitalia rolling stocks. You can reach maximum speed of 350 kilometers per hour.
The Frecciarossa Mille, or Red Arrow 1000, is the latest and most state-of-the-art addition to Italy's high-speed electric train network.
You know, Italian high-speed changed way of life in many ways. People, they used to travel overnight or spend the night in the town. They don't have to do it anymore because they can travel during the day thanks to the real journey time between Rome and Milan or Naples.
But how do you create an electric train that is capable of running 350 kilometers an hour and cutting the 579-kilometer journey from Milan to Rome to just 2 hours and 20 minutes? The answer, it seems, is to innovate everywhere.
You know, when you race speed, you cannot single out one item that makes you go faster. So every subsystem of the train had to be thought again, like the traction system, the braking system, communication, suspension. Like every single piece of the train is affected by the way that we want to run at higher speed.
At the Fleet's depot in Naples, engineer Sabato Citro is getting hands-on with one of these super trains to reveal the secrets behind its explosive speed.
For mechanical components, at 300 kilometers, stress is very high, both if the train is going on straight track or is bending on track. So that's why we have safety checks here. We have special equipments to make sure that everything is performing at 100%.
Travelling at record-breaking speeds requires a radical rethink. Most traditional trains consist of a single locomotive that tows a string of free-rolling carriages behind it. That means all the power is on one spot. Fine for a slow train, not so fine if you're in a hurry. The Frecciarossa Mille completely breaks with tradition.
When you have a train very powerful and very light, you need a special balance between grip and power. At 300 kilometers per hour, the friction between the wheel and the track is very important.
This remarkable train does away with the usual locomotive altogether.
Normally, a traditional train would be powered by a locomotive, which is a special coach, inaccessible to passengers, with all the system, high voltage system and traction system. While here, using 16 engines, we are using the grip of 16 wheels. This engine has a power of 600 kilowatts, which added to the other motors of the train gives a power of 10 megawatts, which is also compared as 100 cars.
Having electric motors spread along the length of the train means more even and efficient traction. It also means that, instead of a giant powerhouse at the front of the train, there is now just the driver in his high-tech cab.
If you have a loco, you just carry one person, the driver. In this train, we don't have a loco. All the equipments and subsystems are distributed along the train, so we can provide at the same length more people on board.
But carrying all those people in comfort at up to 350 kilometers per hour throws up even more challenges.
One of the great advantages of train compared to airplane is that when you travel, you can work. So when we race speed, one of the biggest effort we have to make is to keep the comfort as was in the past. If we don't provide a good subtraction system, it would be like going on a roller coaster. You have very high speed, but no comfort at all.
An uncomfortable passenger ride is usually down to one of, or a combination of, three things. Bumps and vibrations transferred from the wheels to the bogie. Bumps and vibrations transferred from the bogie to the passenger carriage that sits on it. And centrifugal force when a fast train is cornering. The solution for the speedy red arrow lies below the passenger's feet.
This is the bogie of the Frecciarossa Mille. It's connected at this point here to the coach. As you can see here, we have a primary suspension with two springs suspension, which are almost the same used in the car. So here we have the secondary suspension, which is basically an air ball, so it's filled by high pressure air. And this one is very important because it absorbs all the energy, all the vibration in between the bogie and the coach. So this one is essentially the most important one for the passenger comfort. If the train takes a bend on the left, the centrifugal force will push the train and passengers on the right. So controlling the air pressure in these airbags, the train can lean on the left side, and that compensates the centrifugal force without slowing down. This one is the ALS system, the active lateral suspension, that works like an arm and keeps the center of the coach in the center of the track. At 300 kilometers per hour, the vibrations are very high, so all the suspensions work together to absorb all the vibration and to make sure that the comfort passengers on board is at the top level.
The multi-layered suspension system makes regular adjustments as the train hurtles between Italian cities.
You don't feel the speed. When you check from the screen, say you're going 300 kilometers per hour, you say, no, it can't be. It's as if you're standing, as if the train is still. You don't feel the speed.
Every aspect of the train from top to bottom has been interrogated and designed for optimum speed. The electrical systems are cutting edge. The joins between the carriages have been covered with aerodynamic rubber, and the entire train has been constructed in the lightest way possible. But all these speedy solutions can create the potential for a dramatic and unwanted side effect. When travelling super fast, a train's cab shape is key. A refined nose may look the part, but if the wind's blowing from the wrong direction, even this can be prone to lift. If the engineers of the super-fast Frecciarossa don't get its front right, the train simply won't stay on the track.
So the special profile designed for this train make the aerodynamic resistance very low at 300 kilometers per hour. The airflow is going on the top of the train, and then here, as you can see, the flow goes under the bogie, thanks to this part here of the profile.
Likened to the neck of a king cobra, this unique flared shape crucially reduces aerodynamic resistance, as well as improving stability, allowing and contributing to the incredible speeds, the full appreciation of which is usually reserved for the driver, positioned in the Cobra's head.
For me, that I'm not a driver, it's always, very amazing to be in the cab. Lets you feel speed, seeing all these posts coming at you very, very fast. The aerodynamic of this train is unprecedented in other projects because this train was designed, built and tested to run at 350 kilometers per hour, so aerodynamics was one of the key factors in building it.
Today, the designers and engineers of the Red Arrow are achieving the impossible.
Thanks to the high-speed trains, we had the chance to change the way of living here in Italy. People can afford to live in Naples and work in Rome. People can afford to live in Turin and work in Milan and vice versa. It's all thanks to the high-speed trains. It's 12 years I've been working as a conductor, and I've worked on a lot of trains. Once we had this train, it changed our way of working.
This is one of the most impressive trains in Europe. I'm very proud of being involved in this project.
Seeing on the tracks and running at such speed, it's a great feeling.
Since the first trains took to the rails, engineers have been driven by the need for speed.
The A4s, they're built to be faster and more powerful. They are the ultimate express passenger locomotive design.
Striving for this speed, they've produced extraordinary innovations.
We thought of having a train that was a breakthrough in railway technology, and now we have it on tracks. So it's really important sometimes in life to make a step forward, not to follow technology, but to set a way.
Breaking records across the globe.
The 500 Shinkansen sleds also could be the most epoch-making rolling stock in the railway rolling stock's history.
And they continue to push the boundaries to create more impossible railways.